Everyone, welcome to the course of Computational Fluid Dynamics. This is Unit 1, and in this unit, we will learn about Navier-Stokes Equation and its application. In the previous lecture, we have talked about Reynolds transport theorem, how it connects to the system to control volume, about the mass momentum conservation principle, and then we derive the continuity equation. The objective of today's lecture is to understand the Navier-Stokes equation and different terms occurring in it, and the application of Navier-Stokes equation on general bearing. So Navier-Stokes equation is basically the application of Newton's second law on a fluid particle. So suppose if you take a fluid particle, a control volume, a very small control volume, then summation of all the forces acting on it can be given by the rate of change of momentum of that fluid particle. And we know the names of the forces acting on that fluid particle. That is gravity forces, pressure forces, viscous forces, and other forces. These forces can be basically categorized into the body forces, which act upon the whole control volume, and the surface forces, which acts upon only on the surfaces of the control volume. For example, pressure force and viscous force are the surface forces, and the gravity force and electromagnetic force which act upon whole of the body can be thought of as a body forces. So if you derive these forces, then the following equations for incompressible flow comes into picture. So del U by del T equals to minus U dot del U nu del square U minus 1 by rho del P plus F. F is the body forces. So if we expand, then we will get in each x and y direction the related differential equation. So remember, this is a partial differential equation of second order, and for the constant property and Newtonian fluid, we can have this form of equation in x, y, and z direction. So these equations have four components. We will tell you about this in the next slide. So the first component is change in velocity, which is a advection term, which means how the fluid is pushed into the flow field. So this term is given by U dot del U. The next term is viscous diffusion. If the properties are constant, we can take this nu outside of the derivatives del operator, and it becomes nu del square U, where U is the vector, velocity vector. So this controls the velocity diffusion, and these terms explain how the fluid motions and disturbance is damped. The next is the pressure force or pressure gradient. So that depicts how the fluid moves from high pressure area to the low pressure area. And the fourth one is body force term, which is usually gravity, which acts upon whole of the body or the control volume. The application of Navier-Stokes equation can be found in general bearing. In general bearing, there is a shaft about which a thin layer of lubricant is placed. The shaft is rotating, and so is the bearing rotate. So the efficiency of power transmission can be calculated using the pressure developed inside the lubricant layer.